Yeah, so some more participants will be joining, but that's okay. You can carry on.
So I'm still on the screen, so I think.
Yeah. You have to share your screen and then.
It is, can you see it? Not yet?
No, not yet. Yeah, you can go ahead.
So, good afternoon, everybody. So we will continue where we stopped, from where we stopped. And we started with, we stopped, I think, at this position. And here I put also one figure to show how the particle moves. In the case we have a jetting cross flow. This was a rough calculation we did in the past. So we see that the particle try to follow the gas phase 2 if the Stokes number is very small. So we introduced this part here, and what I didn't put clearly is how we derive this part here, and I show now here how we did it. We have the mass transfer per unit area per unit of time. We have the mass flow, the flow rate multiplied by the surface. So the interface here, what we have the velocity of vapor, and we have a density of the interface, and it moves or it go down due to evaporation, and S is the surface of this. And if we take it per unit of surface, we have capital M dot, and it is the diffusion coefficient, what we have here, divided by the multiply by the variation of the density along this this direction. It is the direction orthogonal to the interface. And if we divide everything by this quantity, okay, so we multiply by this quantity and divide by the same quantity. We have the mass fraction, and this is this mass fraction we had. And if we calculate the mass transfer now, if we assume that we have this interface, we have this ratio or this difference similarly to what we had here, and it is the result that is what we obtain in a similarity to this, the mass transfer, like the heat transfer, and here we have the mass diffusion, and that is what we obtain exactly for this mass diffusion. And we can now couple by dividing this by replacing the mass transfer coefficient by this quantity where we have now the Sherwood number, we have obtained this quantity here. And if we multiply by the surface, the interface surface, then we have the mass transfer per unit of time, that is a mass per unit of area and time. We have this variation, that is the evaporation rate, which is obtained in this way. And having this quantity very far from the interface and this mass fraction at the interface, we have this difference, and we can say if this quantity is small compared to this one, we have evaporation, and if this quantity is larger than this one, we have condensation. And that is what we did then in the in the previous lecture. And we obtain at the end the ratio between the thermal relaxation time and also the dynamic relaxation time, and we obtain that here for the liquid, the velocity equilibrium is achieved much more rapidly than the thermal equilibrium, as we see here, with respect to this ratio, which is very small. Now, let us continue with this interface coupling. We have the mass coupling, as I told you, that we have also momentum coupling, and also we have also the energy coupling. So we consider that the mass coupling is due to the interaction of mass between the carrier phase and the disperse phase. Let's consider a control volume here. We have this control volume here zoomed. So the particle, the carrier phase has this density and this velocity. It goes through like this one. And we consider that the droplets are evaporated to get this interface, this coupling with respect to the mass. And the mass generated by unit time by droplets will be this mass fraction what we had multiplied by the number, the density of particle multiplied by the volume. The volume is the L exponent 3. And the mass flux through the volume should be only this quantity here multiplied by the surface what we have here. It is L exponent 2 multiplied by the momentum. And the mass coupling is the ratio between both, between the mass generated per unit of the mass by droplets divided by the mass flux through the volume, or we can say scale by the inflow conditions. And this quantity, this coupling, can now be written in this form. We replace this quantity in this expression. We have the first part here, we have the denominator here, and then we multiply both by now we get here, it remains only L, so the dimension L, we have N multiplied by M, and we divide only by also by M. And this quantity is no more is what we got before. It was the mean density of the flow of the particle divided by this quantity what we had here, and multiplied by the rest what we have. And here we have to assume that we consider the mean value and not the specific value of each particle. So now, if we define the Stokes number based on the mass, we have introduced this the dynamic Stokes number. We introduce also, it was based on the ratio between the dynamic particle relaxation time and the characteristic time of the flow. Now we introduce here the Stokes number based on the mass transfer. So the process, the characteristic time of this process divided by the characteristic time of the Fourier phase, and this time is only can be characterized by the mass divided by the mass rate or the evaporation rate, and it is a time. And if we consider what we introduced before, it was this concentration, the ratio of this divided by this, then we include everything here. Then we see that the first part is this concentration, the density, the concentration, and then we have the inverse of this Stokes number based on mass and multiplied by this characteristic time for the flow. And we replace everything here as we have, and we can now introduce the Stokes number based on the mass, and we have this ratio, which is here, and we obtain that this concentration, if we say that it is equivalent to the mass loading. In this form, we have gas particle or gas droplets, so we have the mass loading. Then we can say the mass coupling is proportional to the mass loading divided by this stochastic, by this Stokes number based on the characteristic time of the mass coupling process. This is the first part for the mass coupling. We can do the same for the momentum coupling. It will be also defined in this form: momentum generated by droplets divided by the momentum flux through the volume. It is exactly what we did here. So the mass generated by droplet divided by mass flux through the volume. Here now the flux is our momentum, and we have to define this. So first we introduce the drag force as we considered before. We have the relative velocity. We have also the drag coefficient. We multiply by the density and also by the volume. And we have the momentum flux through the volume. It is our momentum multiplied by the surface. This is what we have there. And we put everything in this expression. We obtain exactly what we have here. And if we consider that m, the mass, divided by the dynamic relaxation time, it exactly this quantity here, then this quantity can be replaced by this one. And we know that what we, from our notation, this particular relaxation time is equivalent to exactly the dynamic relaxation time. And we know that the corresponding time of the flow is L divided by the velocity. And we had also introduced this concentration. We put everything here, we get exactly what we have here, so that we can replace this quantity by C. If we replace this quantity by C, this is the characteristic time of the flow divided by this. We have the Stokes time, the Stokes number based on the dynamic particle relaxation time, and we have 1 minus this quantity. So this is what we obtain from the momentum coupling. It is related to the stochastic number, Stokes number based on the dynamic relaxation time. And this one is related to the Stokes number based on the mass coupling process. But this expression is a little bit a problem, because if we assume that the Stokes number goes to 0, this means that the velocity of particle goes to the velocity of the flow. And it is, if this is the case, then we will have here 0 divided by 0. So we see here it will give 1, and it will obtain 0 divided by 0 here, and that is not what we want to get. For that, we modify a little bit this expression, and to get it correctly, so we introduce the expression we obtained before, as we have introduced this quantity, the dynamic relaxation time. We did it for the Stokes flow case, where the Reynolds number is very small. We have laminar flow, and we got F. It was this F, I think you remember again. Excuse me. So we have this F. It is this quantity, the drag coefficient multiplied by particle Reynolds number divided by 24. And if we put this equal to 1 for Stokes flow, this means that the Reynolds number is a constant. The drag coefficient is 24 divided by particular Reynolds number, and we obtain this expression. This is the expression we use now in the case where we have these difficulties, this difficulty here. So we use this expression. This is the particle velocity, that is the flow velocity. So we assume now that the droplet velocity is proportional to fluid flow, not equal. So this means that we have a constant lag solution. So C, we introduce C, this is different of the C we have introduced for the mass loading. We put this as a constant value. Then we can write this expression here like this, because we have U equal, a little bit equal to this. Then we have we can replace V by this product here, pi multiplied by U, and we have this quantity equal to this divided by this, and we have a 1 minus. And if we calculate this, we obtain it is equal to this. Okay. Now we say that this quantity here, 1 minus P, is equal, what we assume here is now, we put this quantity is divided by phi here. We have this, and it is equal to this one. And from this, we obtain the ratio between these two quantities. We have the Stokes number based on the particular relaxation time or the dynamic relaxation, particular relaxation time. And for that, we have the Stokes number here. We add 1 and on both parts to transform it correctly. Then we get from this transformation that phi is equal to 1 divided by this sum here, what we have. Then we can say that this momentum coupling parameter, which is here, where we replace this ratio by phi, as we had here, and we have now the expression of phi as function of the Stokes number, and we can now write this in this form where we replace phi by its quantity here. Then we obtain that the momentum coupling is proportional to this concentration divided by the Stokes number based on momentum transfer plus 1. And if we say that this concentration is proportional to the mass loading, and we see that this momentum coupling is proportional to the mass loading divided by this. And for the mass coupling, it is only divided by Stokes number based on the mass coupling. This was for the momentum coupling. Let's see now what happens if we deal with the energy coupling. The definition is similar. The heat transfer from droplet to fluid divided by energy flux of fluid through the volume. And here we assume that we consider first a control volume to see it correctly. So we have the energy flux, this flux multiplied by the surface L exponent 2 and to multiply by this energy. And this is the heat transfer we got as we have introduced the Nusselt's number. I think you remember it. And it is exactly what we had here to have a correct idea of this. It is exactly this, and this is exactly this quantity. So we have this, and that is what we use now at this position. So we put this quantity divided by this one, and assuming the expression we had before, we multiply by m, we divide by m, and also some expression here. So we get L. We have L here divided by U, and we have also the relaxation time, the thermal relaxation time we have introduced due to this quantity here. And at the end, we have the difference of the temperature on the droplets and in the fluid phase divided by this quantity here, what we had. And if we assume that this one is our concentration, which is proportional to Z, and this is our characteristic time of the flow field divided by the thermal characteristic time, and this will give us the Stokes number of it will give us the Stokes number of based on the thermal characteristic time, and we consider also that this quantity as we have tau. We can introduce here also the ratio we obtain, I think. So we can use this expression here. And there we get now this not as function of the thermal of the Stokes number of the energy coupling, but as function of the momentum coupling here. So the Stokes number of the dynamic Stokes number, we can say, and it is equal to what we obtained before. We have that the mass, the momentum transfer parameter is approximately the same that the approximately the same as the energy coupling parameter. And it is in the case we have the Stokes number equal to going very, very small as we did it in this case. This is an expression for this case, but in the general case, we have this expression here. So in the expression, in the general case also, we'll get this expression here, but for Stokes number going to very, very small, we get that there is a proportionality between these two, and this is approximately the same length. For notation only, so F, it is for the fluid phase or the gaseous phase or carrier phase, it is the same notation. To sum up, in the case, the mass transfer coefficient, the mass coupling is very small or are very small, all three, then we say that we deal with one-way coupling as we had only this one-way coupling. If there is a coupling in this area in this term or this one, we have a two-way coupling, and we can have also four-way coupling if there is in addition the droplets or particle-particle interactions. So at this point, I would like to make everything together. So we have the one-way coupling, the two-way coupling, and the three-way coupling, as I told you, because here, if we have a little bit the interaction, if the particles are large, then we have the wake flow, and this wake can also influence the flow field behind the next the next particle, so that we have three-way coupling. And four-way coupling, we know that the ratio between the interparticle space divided by the dimension of the particle is less than 10. Then we have the two-way coupling. Or if the volume, the particle volume fraction, the volume fraction of particle is less than 10 exponent minus 3, as we have seen. And we did it. And here we can now introduce some new aspects. In this way, as we explained it before, in this part, we need, in addition to what we have here, for example, the dispersion process, here we need also the modulation process. This means the variation of the particle of the turbulence of the liquid phase, of the carrier phase, due to the presence of particle or due to the presence of droplets. So, and if we have evaporation process, then we have evaporation model. We will come to this later in the next next chapter, where we will deal with the phase change process, and we will see how we can track the mixture formation by introducing some mixing heterogeneity model, and also at the end we will also consider combustion model. And here only to see how the effect of Stokes number acts on the process on the transport of particle. Here it follow the fluid flow, and here it is not influenced. The particle is not influenced by the flow field. So there are also some other parameters, but this parameter is exactly what we obtained before. So it is a length scale, and this is a characteristic length scale of the particle, and this is exactly what we say. It should be, the inverse of this should be smaller than 10. And also Kawa introduced also this one, in which they introduce, beside this quantity, also the fluctuations of the fluid flow to account for the effect in the effect in the case we have particle, in the case we have this process where we have fluctuation of particles of the flow field. Here, this example I gave them before, and for particular systems, for example, in cyclone, we have the particle volume fraction. It is in the order of magnitude. This corresponds to diameter of this range. We obtain this very, very simple if we use the formula we had. L divided by D is approximately equal to 10 if we have, we say that the particles are isolated. We have fluidized bed, so this quantity here is range between these two values, so that the diameters cannot be outside these two values, these two values interval. So we have spoken about these prediction, these processes. Yeah, the particles are larger. There is prediction of turbulence. If particles are small with respect uh, to the structure, to the length scale of the fluid, so we have dissipation of turbulence, and this has been uh, obtained, has been also observed experimentally by Gore and Co. in 1998, 89, excuse me. We have the change in turbulence intensity here, and here we have this ratio what we had. So this is the inverse of you had. This means that at this position here, so we have diminution of the turbulent intensity. And from here to large values, we have augmentation of the turbulent intensity. It is exactly what we obtained. And we did also the same at our institute. It was channel flow. It was a pipe flow. And we here to show only that the energy spectra for a singular phase turbulence flow is almost this one. So we have the part with the energy containing range. It is our integral length scale, and it is the region of inertial range in which we have the slope here, exponent minus 5/3. And here we have the dissipative range Kolmogorov length scale here. So if we have a particle in addition, then this energy spectrum will be also changed. This is what we obtain here. It is the case first where we have no particle. We obtain this energy spectrum. And with particle, so we have a diminution of the energy, of the quantity of the kinetic energy. This was this. We did this also numerically. We obtained this with LES, in which we introduce a model we have developed. I will show you this model in the last part of this lecture. So we obtain exactly first this behavior with particle, and here we obtain the behavior with the particle, and we see that the model could capture very well the variation of the turbulence intensity of the gas phase. So we are dealing with characterization of spray system. We have introduced some parameters. Now, if we have a jet, we have a spray coming from this nozzle, in which we have, for example, also needle movement. We have a sac here, and we have the injection hole, and we have our spray there. As we said, we have different region. We have the dense region, we have dilute region. So in this dense region, we have the primary breakup, so the first part of the atomization of the spray formation, and the first ligament which are formed, so disintegrate further, and we are in this region of secondary breakup. In this region, we have droplet collision and coalescence, and we see that in this region, we have really four-way coupling. And further, we have the dilute part, and there is more probability to get evaporation. And if we have the wall, then we will have wall impingement of the spray wall interaction here. And the global quantities we can get here is the first one here is the spray penetration. So how long the spray can penetrate up to this wall impingement. This is the spray penetration, and also the spray spread, in space. And we can have also the so-called the spray cone angle. This is this one, and they are the characteristic of our spray. We can also have some problems within the nozzle if the inflow pressure is not equal to the outflow pressure. And then we have some difference of pressure here within the nozzle, so that this can lead to some cavitation. And we can also build some cavitation parameter here. But here I show only that the static pressure is different if we have a turbulent flow, a correct turbulent flow, and if we have some variation of the pressure here, then the static pressure will be different within the nozzle. To sum up, if we have a spray injection, so we can observe 5 essential sub-processes. We have first the breakup. So outside the nozzle, here we have the internal nozzle flow. We have the primary breakup, and we have the secondary breakup. We can say this is the process of atomization. In this area, we have droplet collision, droplet coalescence, as we said. And after that, we have this part, build this dense region of our spray, and the other where the particles are really dispersed. We have dilute region, and where also the combustion can take place. Sometimes also here, but these are issues we will discuss later. We see that we have the breakup atomization process. We have phase change with evaporation, for example. We have transport of this particle, so dispersion, and they interact with the turbulence, and we have a mixture formation. We have combustion, as we have seen previously. This is very complex multi-physics and a multi-scale process, as we have seen before. To get a very good insight on this, it is better, suitable, and can say efficient to carry out so-called hierarchical modeling. This means we will start from simple configurations and then increase the complexity to include more phenomena. That is what we will do in this lecture. So I will answer, I think, to this question later. That is the question, let me read it. What is the significance of the coupling when Stokes number is larger than 1? This means the flow of particle is not affected by fluid flow. If the Stokes number is larger than 1, so then I have to go back. Excuse me. The significant. So we are here, or perhaps here. So we have 3 kinds of coupling. So at least, basically, we can also have coupling with respect to entropy, or with respect to the mixing, but to the mixing, it will be related to this. So we have here 3 kinds of Stokes numbers. We have the Stokes number based on the mass coupling. Okay. The Stokes number based on this momentum coupling. And that is, I think, your question. If this is small, then this we have not coupling of the momentum, but we will have coupling on this part here. Then we will have coupling between both, because this quantity will not be zero and this will not be zero. And also, if this quantity is also larger than one, then also the particle will not be influenced by the the particle will not influence their fluid flow, but the fluid flow will influence the particle. Then we have the one-way couple. Yeah, I think you have the answer to your question. In any way, we have a coupling, either one-way coupling or two-way coupling. In this case, we are not here, but we are here. We have this coupling in one-way coupling. With respect to the momentum and with respect to the mass, we have also the coupling. And with respect to energy, it is similar to the momentum. So I think you get your answer. How to calculate penetration length in case of co-flow? Spray and the droplet does not evaporate. The droplet is being carried with. So we will come to this in some application we will see, and everything will be clear. So this means, because we are here adopting the hierarchical modeling, then we have to decompose the different processes. We have here, this part is the dense flow region, and this is the dispersed flow region. So we will focus on this later, and at the moment we will try to focus on this part in the next chapter, where we will speak about the spray atomization, and also on different kind of nozzles. So if we decompose now these processes in sub-processes, we have exactly what I have provided you before. We have atomization in this part. We have spray formation. We have evaporation. We have mixing. We have combustion. And at the end, we have the interaction, perhaps also between the combustion with the flame and the droplets, which is not really really investigated in the literature, but this is also to characterize further our spray. Let's go into details by considering a mesoscopic level. And dealing with the mesoscopic level, so we see that the multiphase flow is normally characterized by droplets or particles, we say, of different sizes. And because this is the case, we have different sizes and we have the amount of this particle, then we have a distribution function, and we can get a distribution function with prescribe this. We can have a function which describe this distribution, and then deduce the moment related to this distribution function. So this distribution function, let us call it f. It is a function of the diameter of the particle, of the position and the time, because if it is evolved, so it display within the space, and also the particle change the size, so that we have a variation of the space as function of the space, of the time, and also of the density of the diameter. We can also go further to say not only for the position, but we have also the velocity. First, the position of a particle, velocity of the particle, the radius, so the size of the particle, the temperature of the particle, and also we can get other parameters we will introduce in along this lecture. So we, if we build this quantity, then we have the number of particles we have in this control volume, and if we integrate this and multiply by diameter and at given exponent, then we have the moment of of this distribution function. And if we let's put k equal to 0, it is 0 here, it is 0, then we have 1, and this gives us the number of particles, the number of droplets. If k is equal to 1, then this quantity is the mean value, the mean density, the mean diameter, and we can also normalize it by the number of droplets, then we have this ratio. If we have here 2, then it is a surface, then it will give us a surface, and we can normalize it also by the number of droplets. If we have 3, so then we have the volume, then we have the volume here, and we can also divide by the number of droplets over mass, so we have the volume. So we will get different moments based on this distribution function. That means that the distribution function, it's a key parameter, it is a key quantity which helps us to define different moments of our spray or of our local distribution function. To get this function, so William developed an equation. So this equation, William's spray equation is similar to the Boltzmann equation. I hope you know this equation. So the Boltzmann equation is specialized to spray, give us the William spray equation. So we say that the equation give us the evolution, describe the evolution of this distribution function. And if we write down the total variation of this quantity is normally equal to 0 in phase space. And if we try to write it in details, so we'll get on the right side, not 0, but we will get so-called the collision integral. And here, in the case of spray, this collision include not only collision, but also coalescence. And it is this part here. And the left part will be the total differentiation. It will be the partial time variation with respect to x, with respect to this, to the velocity of the particle, with respect to the velocity of the fluid phase, and with respect to the temperature. And we have all phenomena here, evaporation, the drag force, and here we have also the change, the evaporation rate. Here we have the evaporation rate is here. We have the drag force there, and we have the droplet particle temperature variation. It is there. It is based on this is the delta T for particle. So it is variation of the temperature of particle. And this is the drag force. This is the evaporation rate. This is the convective part. And it is the local variation of our function. And this one is the collision integral. So to solve this quantity is sometimes time consuming, but there are now methods which help us to solve it. We'll see some of them. And if we solve this, we can get now this function and we put here so that we obtain the moment we are looking for. Based on this, we have one quantity characterizing the average droplet size of a droplet, and this is the so-called the outer mean diameter. The outer mean diameter, I have spoken here about the surface, and here we have the volume. The outer mean diameter will be then the ratio of the volume and the surface. It is the ratio of the sum of droplets volume in the spray to the sum of all droplet surface area. And this is outer mean diameter. If our particle is spherical, and we obtain this quantity. And in details, we have the sum divided by this surface, and it is the expression of this. If we have discrete distribution of particles. In general, based on this, we can also write the generalized mean droplet diameter. We say that this is N and it is P, and we have exactly what we had here. This is N and it is P, and exponent 1 minus divided by N minus P. That is the generalized mean droplets diameter if we have a discrete variation, but we can also have a very nice continuous distribution of this function of these quantities. That is our discrete distribution. It can be normalized, and if it is normalized, then the sum give us the number of particles. And for the mean, as we have defined here, this defined there by giving that k is equal to 1. Yeah, it was the mean. We obtain this in this form. And for the variance, so it is exactly what we know. We have the momentum value minus the mean value square multiplied by the particle size density function. If it is continuous, then we have this. And if we have this, we can also write every so much here as integral. And that is what we have now. Here, normalization is equal to 1. And the median can be written as this one if we have these to the mean values. And the ratio of momentum, that is exactly what we have obtained there. And if we have 3 here and we have 2, then it's the outer mean diameter as we have here. The cumulative function is exactly this. And if we had this different distribution between these two intervals of the distribution between these particle diameter interval.
Excuse me, Professor Sadiki.
Yes.
There are some questions. Maybe you would like to take it up now because this might be related to these few slides.
I think so. The for Robin Kumar, so we'll come back to this. So in chapter, I think where I will show some calculations of this parameter for a realistic droplet for a realistic spray. Or can you explain a bit on droplets called particles? No, droplets. So what I would like to say. So the particles can be droplets. This means liquid particle or solid particle. And in this part, I say particles are droplets. This means liquid droplet. We consider liquid fuel. Okay, this was for Babu Bai. And he has, so is this droplet distribution function applicable to all type of atomizer? I didn't give exactly the form of the distribution function. So we will see, we have to solve the, this equation. And if we solve this equation for different type of atomizer, we'll get the distribution. But there are some atomizer which have prescribed form of this function. So normally we have the Rosen-Lambda distribution function, and I will show also some other for example, the what we obtain for example the nozzle by from Roy, in which we calculate the distribution function and we compare them with experimental data. Is there any relation between South-Tamin diameter and spray penetration length? A direct relation? There is no direct relation, but we can find some correlations, and I will give you also some correlations which can be found. We did also for this jetting crossflow. So I think this was the question by Anurag. Are there some other questions? For Koma, I will come back later, I think tomorrow or after tomorrow. How to calculate? The droplet is being carried with the flow. This seems to be infinite length. No, the length is not infinite. Oh, I understand now the question. So it is now infinite. So let's go through this liquid atomization and spray structures. Then you will understand it very quickly.
Yeah, you can continue. You can continue.
Yeah, I think it is better to see exactly what is here. The penetration length, it's only the length in which we have the spray spreading, and somewhere, so the spray disappear when the particles, for example, or the droplets does not exist. So we can define this and we will do. So let's now go to the liquid atomization and spray structures. We have seen that the spray characteristics strongly influence the mixing and consequently the combustion process. Then it is necessary to get knowledge of the influencing physical phenomena in the spray system. And this is it is very important if we want to optimize the combustion process for in combustion system fired by liquid fuels or by solid fuel. We will see this later on where we don't have sprays. So there is then necessity to get reliable spray simulation tools. So going from this dense flow to the dispersed to this dispersed part of particles. So then we have the atomization of jet and film. What really happened when liquid jet atomize? So we see here from what jet in the shower. So we see exactly what come out. It depends on different parameter, on this length, on the velocity, on the inflow velocity, and on the environment naturally. So what we have here is some kind of this. We have a cylinder, undisturbed cylinder. So this cylinder develops perturbation on the surface over time. And these perturbation grow. And these grow depend on the curvature we have here in this thin part and a large section, which is a function of the perturbation wavelength. This is an explanation if we consider Rayleigh instability. And if this grow further, then and this perturbation with the appropriate wavelengths grow, this can lead to the strait and to break up here. And if this perturbation doesn't correspond to an appropriate wavelength, then this will get the initial form as we have. This means that the fluid jet breakup is is the process in which a single mass like this of fluid break into several smaller fluid mass. And this process is characterized by elongation of the fluid mass forming thin, as we did, as we see here, forming thin thread-like region between large and nodule of fluid. This region content to thin until the break forming individual droplets, as we can obtain from here. But this is really, this cannot help us to make some calculation to characterize the spray. This is why we will go into this process and understand in details what is going on. So we can classify the nozzle because it depends on the nozzle on the nozzle geometry. So that is why we have two types of atomization, which are mostly used. And we have the atomization based on capillary or chaotic breakup of a jet or liquid jet. This is, for example, what we obtain when we have a pressure atomizing, air assist or twin fluid atomizing. For example, a pressure atomizer, simplex atomizer. I will summarize everything in a table now in a few minutes. And we have also so-called aerodynamic breakup caused by the shear stress at the liquid gas interface. We have naturally as a kind of atomizer which use different form of energy, for example, electro spraying, plasma spraying, etc. But let's classify this in these two parts. So we have first the pressure atomizing system. We have liquid phase, which is spray, which is injected at very high injection pressure into the quiet environment. So the kinetic energy acts as energy source of atomization because we have here a very strong interaction between the interface of this and the gas phase, which is almost in a quiescent state. So the velocity of the liquid is very high compared to this. This creates here an interaction, so a shear flow, which is very high. And the other one, air-assisted atomizer, we see that it is air-assisted. This means that the liquid is exposed at high velocity of air, and the high momentum associated with the gas phase disrupt the liquid sheet. And we can put them together. We have the pressure atomizer, and we have also the twin fluid atomizer. So for pressure atomizer, we have the plain orifice, we can have the fine orifice, we have the simplest orifice. So that is the direction of the fluid flow, and that is the duplex. So we have the two. So we have these two orientation of two direction of the flow, of the liquid flow. And here it is the rotary atomizing atomizer. So the flow, the fluid come on this disk, and this is rotating, and this produce atomization. And we have also art of this cup. So this go down, and this is this is sprayed due to the rotation here. So the twin fluid atomizer, we have the air assisted. So the fluid flow comes here, and here we have the airflow, and the interact here for to generate the spray. It is a mixing which take place internally, and this take place externally. Here we have this mixing here, and they take place first here, and then they come out. We have also the air blast. The air blast, so we have in the middle, we have the fluid, the liquid fuel, and here we have the air, and here we have the shear built between these two here, and then we obtain the spray, we obtain the disintegration of this film at this position. We have also pre-filming. Here we have these two liquid, and we have a film, and with this here, this film will be destroyed at this position here. So we will see also an example of this one in some application we will have. So particle spray nozzle, we can classify them in the art. They try to disperse according to a specific desired pattern. For example, holocone, the holocone, so the spray is dispersed in this form, and is the full cone, and here it is a flat cone, and here is conic. So they give you the form we have there, and for each one, it is used to generate a kind of specific droplet size. For example, air atomizing nozzle, they produce the droplets of this size here, and the hydraulic atomizer, produce diameter size of particle of this diameter here, and larger also, and or they can also generate only this part. And we have also the flat spray nozzle. So we have this full cone, first this here, and the full, the flat spray cone is generated by this one. So this means we get the range in which this kind of spray of atomizer can produce for us if we want to get a specific dimension of the spray. We have also other type of atomizer, compressed air nozzle, nozzle for steel works, as I introduced at the beginning. We have also for fatigue nozzle. So different, very, very diverse sort of atomizer. And here I summarize, following the work by Berokal, 2006, the relevant properties of atomizer I will come back to this. Thank you. So let me now go through these quantities. So we have the relevant properties for atomization. We have the injected liquid. We have the liquid flow. We have the ambient gas, the gas flow, and the injector. In which way? So the injected liquid, so we have the surface tension. I will show you now in a few minutes the effect of surface tension, the viscosity and the density, where we will introduce the Weber number. So we have the injection pressure, the velocity, and turbulence in the liquid stream. So these also will be shown. The ambient gas, the gas density and the temperature naturally. So gas flow, the absolute velocity, the relative gas to liquid velocity. So these will be related to the particle Reynolds number and the turbulence in the gas flow. And the injector, so we have the orifice diameter, the internal structure and geometry of the nozzle. And naturally also on the condition within the injector, as I told you, if we have some cavitations. So the geometrical aspects and characteristic of spray, let's see first this illustration. And perhaps the participant who have asked about the penetration length will get, I think, the first reply, the clear reply here. So we have LC, it is the length of the liquid core. Okay, this is the length of the liquid core. And LP is what we call the distance of penetration. This means that where the distance at which we can still have some droplets. We have here the liquid jet or sheet thickness, come out with the thickness of the nozzle. And we have this direction. So we have the radial and we have the axial direction. And here this is the wavelength here. And we have also the cone, a spray angle, what we had, and we have these different quantities. So this means we have first the nozzle flow rate, we have the liquid or sheet thickness, we have these two directions, we have the length scale of the liquid core, okay, we have the distance of penetration of our spray. It is the spray penetration length. It cannot be infinite because the particle somehow disappears. And we will show you exactly how, when we have a calculation, how we can calculate it. So we have also the mean droplet size we have introduced. We have the drop size distribution. This was our F. The droplet number density, our small n or large n. We have the radial parternation, circumferential parternation or radial also. We have the spray angle, we have the evaporation rate, and we have the wavelength as we have. So all these parameters are relevant if we would like to investigate the atomization process. With respect to different pressures, and these, what I sum up here, I will also put them here relating to this paper by Shepard. We have different kind of nozzle of atomizer. and which kind of droplet size they can produce. Here are references. These references are in this paper, but I didn't put the references here. So we have the internal mixing. For example, they can produce between a droplet size between 50 and 500. And also we see the spray cone. We can also produce up to 80 degrees. The external mixing atomizer, so you see here, so the internal mixing and external mixing. These produce this kind of droplet size and may produce also this kind of spray cone angle. If you want to get more spray angle, so we have to use this, or to use the pressure swirl, yeah, because it produces larger and rotary, so produce more ultrasonic, electrostatic, and effervescent. No more. Here we have only up to 23. But here we have the droplet size we would like to get, and the pressure, the injection pressure are also listed here, and we have also the upper mass flow and also the upper viscosity we can produce. Good. These sum up the operational performance parameter and the representative operational limits of these different. Let me now go to we have here some questions. So is the length of liquid core the same as liquid breakup length? Yeah, we can say so. It is the same. We can say that it is the length where the breakup is completed. Then it is the liquid core. And the liquid breakup length, it depends if we are in the primary breakup or in the secondary breakup. So in liquid jet atomization, distribution is coming from nozzle itself or from sharing with ambient. So these may be both. It depends on the quality of your nozzle. So if the nozzle is very good, then not. If yes, then we have also some distribution from the nozzle itself, like cavitating, where the nozzles, we have some cavitations. Then it is already generated within the nozzle. Okay. So let us continue. The droplets being carried with the flow, this seems to. So I think the first, for Kuma, I have give part of the answer. The other one, how to calculate it, we will see later on in the exercise. And also I will show the relationship if it is one. So I will show also some correlation for the impact of the ratio L to D on the atomization. So there is also some correlation we will see. So I will now go to into details. And by taking an example, it is a plane jet, a plane atomization, and it is a pressure jet atomized. So we see that the flow is coming here with this thickness, and we have here the liquid core. It is the length of the liquid core, and we have the multiphase mixing layer. We have the primary breakups, and it go up to here. That is also the length of the dense flow region here, because here we have still a ligament, and after that we have dilute spray, and after that we have dispersed flow, And we can speak here from the length of the breakup if we say that where the breakup process is completed. So the mechanism, the breakup process begins with the development of small perturbation on the free surface, as I told you, but we have some stability curve as function of liquid injection velocity. This is made if we based on the Rayleigh plateau instability. This means that the evolution of the stability of the liquid is a function of the disturbance, and this disturbance, the degree of this is also function of the velocity. And we can get this if we take the Fourier transformation of the disturbance to decompose this arbitrary disturbance into perturbation of various singular wavelengths on the surface of the thread, and this allowed to determine which wavelengths of the disturbance will grow and which will decay in time, as I have shown you before here in this explanation. So with this, let me directly put everything together here. So we have the structure and the nozzle tip. So we have, depending on the jet, this is the jet breakup length, and this is the jet velocity. This means it depends on the jet velocity to get different type of outcome. If the velocity is very low, let's say laminar, so we have no flow, we have no droplets, and the diameter of the nozzle it is, and we have the first formation very, very far from the nozzle. If the nozzle, if the velocity is growing, then we have a laminar flow region, and this laminar and at one up to a given distance, there is the formation of surface perturbation, which lead to droplet detachment that we see. And the phase BC, okay, and this gives us the breakup length where we have the formation of the first droplet. And BC, we have the first wind induced regime, and it is like this part, but further augmented by aerodynamic force at jet surface formation of droplets. And here we can speak about transition region, because from point C, we have directly the turbulent flow region. So here, the jet breakup is very, very small. This is this part here. And there we can get this, the length scale of, we have here the jet, we have the length scale of our, of the core. And here the problem is to get this value here in the case we have turbulent flow. And if we have fully turbulent, develop turbulent flow within, already within the nozzle, then we can have these two kinds of bifurcation. Either we have a CD first here wind induced regime. We have intense perturbation droplets form along the jet surface as well, like this one. And for the nozzle atomization regime, then atomization start inside the nozzle itself due to very high velocity, together with nozzle cavitation, as I told our participant in few minutes. We can also have this interaction between all these additive synergetic effect of high velocity and nozzle cavitation. We have formation of droplet right from the nozzle exit, like this one. And the problem is only to find this part here. So if we have this kind of droplets, if you have cavitation, we have no cavitation, and then we have a very nice building representation of the jet brake length as as function of the jet velocity and the consideration of different aspects. So, and with this consideration, we see that we can also have defined a relevant parameter, and this is what I will do now. We suppose perhaps first your question is what is the meaning of first and second? When the meaning is breakup length depend on nozzle diameter and nozzle length. The nozzle length now, but the nozzle velocity, the flow field, the flow velocity within the nozzle. And we see what was the question again? So the primary, the first is the first wind. So this is the BC induced regime. That this means that we have the higher velocity, and we have surface perturbation, which lead to droplet detachment. If we have augmentation of this phenomena by aerodynamic force, then we have the first one. The second one, we have intense perturbation, and the droplets form along the jet surface as well. So here we don't have a surface, we don't have formation of droplets on along the surface, but here we have this along the jet surface. That is the distinction between them. So let's now go to the Weber number. We suppose that we deal with spherical droplets of this radius here. It is subjected to flow field of this density. So that is the density of the gas flow. We assume that it is gas, but there is no, it doesn't change the generality of the results. And the initial relative velocity is this one. So the relative velocity between the gas and the flow field. The gas flow, excuse me, and the particle. So the droplet is under the influence and the influence of dynamic pressure. Okay, we know this. And the dynamic pressure, we can define it like this. Okay, from our knowledge from the gas dynamic, the dynamic pressure is we can say it is a pressure generated by the kinetic energy, like this, due to surface tension between the two phases. This value may be found from Laplace formula, and this Laplace formula is this one. We know this, where this quantity is the surface tension coefficient. Now, we say that the necessary condition for the breakup to occur, one take the domination of this aerodynamic force over the surface tension force. So this should be larger than this on the droplet perimeter. If we neglect the droplet deformation, we will introduce them later on. We are speaking about the aeroaerial formulation or modeling. the force may be expressed as this. This is our aerodynamic force. It is the drag force, okay? You know it. We multiply by the drag coefficient. And it is the surface tension force. We have this, we multiply by the surface, and we obtain this. In the limited case, so where there is equilibrium between both, so aerodynamic force and surface tension force, this equal to this, bring us to this quantity. And this is dimension, the non-dimensional number. And this non-dimensional number is what we call the Weber number. It is a ratio of this dynamic force divided by the surface tension. This is based on the droplet, this is based on the gas phase density, the flow field density, and on the radius of the droplets. If we can also write this based on the diameter of the particle, in this case it is multiplied by 2. This quantity here is our critical value of the Weber number, which marks the transition from the stable to the breakup regime. Okay, then we can say that the Weber number is a intensity of aerodynamic force relative to stabilizing surface tension force. Okay. Some authors define the Weber number using not the gas, the density of the gas flow, but the density of the liquid. And if they do this, we define this in this form, and we have here, instead of rho J, we introduce rho L, and this is, if we put it as function of this quantity, then we will introduce a quantity epsilon within the ratio of this density. It is this quantity. We say that this is obtained without consideration of droplet deformation. Now we consider the droplet deformation and naturally viscosity effect for both the droplets and gas. And because this quantity can introduce some more dissipation on part of the flow energy as well as on the acceleration effect by the flow. And we know that we can then introduce the measure of significance of liquid viscosity effect. We can introduce this by considering another one, which is frequently used, the Ohnesorger number. The Ohnesorger number is defined as function of the viscosity of the liquid and also the surface tension. We can do it as function of the radius or function of the diameter. And from this, we can then get a correlation between the Weber number, in which we consider this effect, and the Weber number where we didn't consider it. This is for Ohnesorger number small than 10, and this is if we have small than 4. Then we have the Ohnesorger number when we have Ohnesorger number going to 0. This means that we don't have this effect and we have this relationship. Good. The impact of the droplet deformation and the onset of the breakup include the droplet diameter, relative velocity, as well as the surface tension between these two. So we have the droplet diameter here. We have the relative velocity there. And now we have introduced also the surface tension. We have also the surface tension here. And also now we introduce the dynamic viscosity, what we had of the droplets in gas, and we have also the density of both. And this leads us to the diagram which was generated by Onesorga. And this gives us the relationship between the Onesorga number and the Reynolds number. And this allows us to take into account the effect of viscosity here, and also they allow us to characterize different breakup regimes. Okay, and we see that if the Reynolds number is very small, okay, not very small, it is the order of magnitude, then we have the Rayleigh regime. And if it is higher, I mean higher velocity, we have the first wind, and this correspond, these lines here correspond to these values of Onesorga number. And if the Reynolds number is higher, then we have the second wind induced regime, where we have also generation of droplets on the jet surface. And if it is very high, we have directly atomization regime. And that is what try to make this in a nice way as function of non-dimensional quantity. It was as function of dimensional quantity, the jet velocity and the length, the breakup length. And here it is as function of non-dimensional quantities. I give you the Onesorga number here is as function also of the as function of the Weber number based on particle and the Reynolds number, and here based on the gas phase, the definition of the Weber number either as function of gas phase density, of particle density, and here we have the Reynolds number, and this quantity here, the Z, is what we had here. It is the Onesorga number. So another group tried to account for the influence of the ratio of the gas phase and the liquid phase. And this allowed to get this 3D diagram. We have first what we had here, Rayleigh, induced, and atomization. So if I put these two together, we have this, and this line is this one here, and this line is this one, and we have the atomization. But they try also to put, to take into account the effect of this ratio, and by taking this effect, and we obtain this set here. And from that, we can also get a relationship between Z and this ratio, and we get this expression there. So to sum up, we have the Weber number. It's a measure of the intensity of aerodynamic force relative to stabilizing surface tensile force. The Reynolds number we know, it is a ratio of the inertial force to viscosity force. The Onesorga number is the effect of the measure of the effect of internal viscous force within the deformation. So internal viscosity with respect to this within the deformation flow, which is due to the the surface tension. So this led me to this breakup regime of liquid droplets. I don't know if it is time now.
Yeah, I mean, you can take up the question and then you see how.
Yeah, let me see if I can continue this. If it need more explanation. So I think I can, let me complete this transparency, this slide. So we have then, based on the Weber number, we can classify different sorts, different art of breakup due to the interaction of the flow field and their liquid. And we have for small Weber number, this means that we have this means that we have also the relative velocity is not very high. Then we have this so-called vibrational breakup. This can lead to this disintegration. So between 12 and 50, we have the back breakup, and we have the first deformation. The deformation, we have the back broke, the back burst, and here we have the rim breakup. So the back and stomach breakup, if we are between 50 and 100, and we see that this breakup, so we have first back deformation, and this come down, this come out, and then they can grow and break up at this area. We have also sheet splitting between 100 and 300, and then give rise to this kind of disintegration. The wave crash splitting is this one here, and this disintegrate in a way that we can say that we wave development, and the catastrophic one is really this, and it's decomposing this, and we have first, and we have this disintegration of this part give us this particle. So this is what Fate proposed in 2002, and we can see also how we can account for this kind of disintegration in if you want to include them in the modeling. So tomorrow we will continue with this by saying how we can introduce this physics in modeling, and we can propose some, we'll see how the literature propose some disintegration, some breakup models. And here I show again how we can see this type of breakups. And we have catastrophic breakup, this one here. And here we have the stripping breakup. This is this one. Show it now in clear way and the background. So, thank you. Let me now go through the questions. So the first question by Robin Kumar. So one part is answered, the other one will be given tomorrow, I think. We say first that the droplets, the penetration length is not infinite. It is a finite length. And we have seen the evolution of droplets at a distance where we don't have no more droplets. Okay. So we will put some statistics to show you how we can calculate it. So this also I will show tomorrow for you, Anuhat. And Kamal, what is the meaning of first? So I did it. And Kamal, another question, first, the relation between honest organ is limited to 610, or we can go till 0. If yes, then why we are using second formula? I don't understand this, but let me go back. Okay. So you say, so the Weber number and Ohnesorge number, and the Weber number for Ohnesorge number small than 0, going to 0. So we are in this area. And the question is now, I would like to understand the question.
Well, you can unmute and then we.
Hello.
Yeah.
Actually, sir, in the second formula, when OH number is less than 4 and the first formula OH number is less than 10. So first one can also be used for the less than, like 4 will become below 10. So we can use the first one also for the same, or it is restricted to from 6 to from 4 to 10. First one, OH number value. Because we can go from like 4 is also below 10, and we can go for 3 from first formula also.
So we have the first relation, it is between 6. Oh, we can go to 0. And no, yeah, this show that this one can go up to 4.
4, yes.
Okay.
Okay. Thank you.
So the other question is, I have a doubt related to the regime diagram. This regime is standard. If I calculate on Zagar and plot it on log and compare with standard regime diagram, so can we say in which regime my case is failing? Yeah, I can say yes.
Okay, thank you.
Yeah, I can say yes. So that is why I provide these two kind of diagrams. So you can put in this one, or you can put in this one if you would like to get in the relationship with respect to the density ratio, or to this one. This is the classic one. So what we have here, it's a classic one, but this one is an extension of it. And if you have a case, you can calculate and say that it is here or there. So we did it also in some papers. I will give you perhaps some references.
Thanks.
So
yeah. Any other questions? I mean, you can raise your hand and I can allow you to talk. Or you may like to type in the chat box. Yeah, so who's this? Let me see. Okay. Yeah.
are there some other questions?
Yeah, Siddharth, you can unmute yourself.
We have still some 4 minutes.
Siddharth, you need to unmute yourself, then you can go ahead with your question.
So if not, so we will start tomorrow with.
Well, there is a question. I think the.
Okay.
Yeah, you go ahead. Siddharth, we can't hear you. He's unmuted. Can you type the question?
So I cannot hear you.
Yeah, I also can't hear. Okay, so the question has come. Yes, so he's typing. Let's see.
Okay.
We have it now.
The relation between injection pressure and breakup length. injection pressure and breakup length. So so I think if I understand the question, it is to go to what I put here. I didn't put the relation, but we can found a relationship between the penetration length and the pressure, injection pressure, and also with the spray cone angle. But I didn't put that here. And the question if I can provide it. So I will provide it. Yeah, okay.
So any other questions? Anyone? Okay. So I think there is no more question. So we can. Okay. We can conclude today. So yeah, the plan for tomorrow. So you will start and then I will take it up.
Yes.
Okay. And then I will finish till day after tomorrow, the first 1 hour.
Yeah, tomorrow. So I have to finish it.
Yeah, you take 1 hour.
Yeah, 1 hour.
Yeah, then I will do 3 hours and then day after tomorrow, I will take 1 hour, then hand it over to you.
Okay, you will start, huh?
Yeah.
Okay, good.
Okay.
Very nice.
So, I mean, that means tomorrow, once you finish your lecture, then you may not need to be here because I will conduct the rest of the session. And day after tomorrow, you may join after 1 hour. I mean, around that time.
Good. It is nice.
Okay.
Let's go in this way. So I know these open questions so that
Yeah, let's conclude this.
the people want to. Okay.
Okay. Thank you all. Thank you. So we'll come back tomorrow.